Hello, linear algebra student. This video is for chapter 1.3. We are looking at vector equations, looking at something other than system of equation or matrix, but something called vectors. And then you can see that vectors is actually to study vector, we can also use systems of equations. So they are tightly related. So you can say this is an application of systems of equation. So first of all, what is a vector? Vector is actually a column matrix. So if you have a matrix that's only have one column, that is a vector. So the simplest one would be a column vector that has two entries, 3, -1 like that, or 2, 5. And the way we represent them would be by bold letter or a letter with an arrow on the top. So usually when we write, we use the arrow. When it is in print, we use the bold. Okay, so when we have a vector, what can we do? So algebraically, we can add two vectors together by adding entries, corresponding entries together. So if I have 3, -1 plus 2, 5, then 3 and 2 add together is 5, -1 plus 5 is 4, like that. We can also multiply it by scalar, each vector by scalar. So if I say C times U, then C would multiply to each entries in the column. Um, so these are the two operations. Geometrically, you can look at a vector as a arrow-shaped entities where it starts from 0, 0 and it ends at the number that we use to represent it. Okay, so like the entries in the column vector, it would be the end of the arrow. It can be used to represent force. It can be used to represent velocity. A lot of application in physics. So if I have a vector x1, x2, it is called a directed segment, meaning there is an arrow that point to the direction where it's going. It's from 0, 0 to x1, x2. If I multiply a scalar by c, then I would make this vector longer, keeping the same direction. So for example, if I have u like this, 2u would be a long vector like this. And then -2/3 would be a vector in the opposite direction of u, but of the length 2/3. So that's how you deal with opposite vector in the opposite direction. If you have two vectors and you want to add them together, we use a parallelogram law. It's kind of, so if this is u and this is v, technically you should say u first. U plus v would be, you go from 0, 0 to u, and then from u, use the same vector to v, right? So this v, so you end up standing here. So this is u plus v. But technically, you can also draw a parallelogram. The fourth vertex of the parallelogram is u plus v. Okay, if you're adding two vectors, both of them starting from 0, 0, you can do it that way. So the sum of the vector correspond to the fourth vertex of a parallelogram whose vertices are u, 0, and v. Okay, so so here this is 2, 2, 1, -6. Whoa. Displayed above. I don't think there is 1, -6, but anyway, if I have 2, 2 and -6, 1, u plus v would be 3, -4. So I can draw the picture. Well, yeah. I don't think this is related to this, but anyway, let's draw the pictures of uv, where u is, let me draw the picture, -1, 2, -1, and then up to. So this is u. V is -1. No, -3. 1, 2, 3, -3, and then -1. So it's this one. So the first is u, the second is v. So to draw u plus v, unfortunately I cannot change color. I wish I could. So you would draw a parallelogram, right? So use this 2 as the side. So you draw the fourth vertex. So this is u plus v. That's very easy. What about u minus v? U minus v is actually u plus -v, right? So I need to draw -v. So v was this way, -3, -1. So the opposite of v, it would be here, 3, 1, right? So this is a negative v. If I do u minus v, it would be u plus a negative v. So I draw the parallelogram. This would be u minus v. So that's how you can add vectors by algebraic method. I think this is not displayed above, but algebraically, okay? Algebraically. Algebraically, you can actually add vector by adding the entries. You can also draw pictures. Okay. We can extend column vector to size n. Instead of 2 entries, we can have n entries. So u could be x1 up to xn. It could be 3, 4, any numbers you want. And a vector can have entry that are all 0. So we call it the 0 vector. So basically it's 0, 0, or 0. And after this definition and the operations that we talked about, we have these algebraic properties of vectors in Rn. So if you have all these vectors in Rn and a scalar C and D, then you can see that this properties holds. If you add 2 vectors together, the order doesn't matter. The associated properties also hold. You can add anyone first. You add 0 is the same as the original. If you add a vector with -1 times it, then it becomes 0. So negative u is -1 being a scalar times u. And 1 times u is just u itself. C and D multiplied to u and v is just the same as individual multiply. C and D add together first before they multiply is the same as you multiply later, if you, or you multiply together. So these are kind of like the basic algebraic properties. The important thing is about vector is I have so many different vectors on space, right? So you can just geometrically, you can see, oh, I can draw any vectors I want. All the points that on the plane can be a vector because I can draw from 0, 0 to them. So, and I can combine them by multiplying with scalar. So if I can actually say I'm going to use vector 1 plus vector 2 plus vector p times c1, c2, and all of them and add them together. This would be called a linear combination of the vector, and it become a new vector. Say, for example, you see how u and v is here. This is u, and this is v. And so u is here, v is here, and you can see that this is 2v. So all this line that you draw parallel to v would actually show how v's direction goes. So you can go anywhere you want if it is an integer multiples of v on the grid line, on the grids, right? And u would be this. So you can see b is at a grid level. So how do I represent b as a linear combination of u and v, meaning how I can get to b using just the u and v vector? I can imagine me doing u one time, u second u, and then go back v, right? But v was this direction, so this is -1v and -2v, right? So all these points on the grids are linear combination of only u and v. Try to do a linear combination to represent n. Where is n? I don't see n. Let's just do b. I think I don't see n yet. Okay, so let's do b. So we say b is equal to u plus u, u plus u, and then minus a v and minus a v because you go to the v direction but backward. So that is equal to 2u minus 2v. So if you introduce 2 vectors, theoretically you can actually represent anything using the linear combination. You may ask, what about y? Right? Y is not on the grid, so how can I get to it? You can get to it by going just not the full v vector, but half of a v, right? So let's say we go to u first, negative u, and then 1v, 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 half v, right? So we would be negative y would say equal to negative u, and then plus, say 3v plus and a half v. So it'd be with negative 2u plus 3.5 v. So likewise, you don't have to, like the point, the vector that you want to produce doesn't have to be on the grid or on the line. You can have it anywhere. So say, for example, I want to have my vector terminate here. How do I get it there? I can actually just go to v first and then go like half of v or something, and then go partial u, right? So long as you draw a line that's parallel to the u and v, you can just do any combination to get to those according to the uv definition. Of course, integer combination of uv will be on the grid point, but non-integer combination can also be done. So that leads us to think about if I have two vector or three vectors or whatever vector, can I, and then a third vector, can I use a linear combination to get to B? Okay, so this is different. So this is 3 entries. Can I use two vector of 3 entries to get to B? So this would be actually thinking of how many A1 do I have to add, and how many A2 do I have? This is A2. Did I have to do to get to B, right? So it become a X1 where X1 and X2 is an unknown in the combination. And if I know X1 and X2 and they equal to B, then it is possible. So basically, it's actually kind of like solving a vector equation. This is a vector equation with two unknown, with X1, X2 being the unknown, right? We don't know how to combine A1 and A2 to get to B. So sometimes we call it weights, sometimes we call it the scalar multiplication. So write it out, the vector itself, the vector equation become x1, the whole vector 1, negative 2, negative 5, plus x2, the whole vector 2, 5, 6, equal to 7, 4, negative 3. And you can see, you can write this, actually this is equivalent. This is equivalent to a systems of equation. A vector equation all of a sudden become a systems of equation because you can multiply the x1 as a scalar into the vector entries and equate each entry to the left-hand side, to the right-hand side. So x1 times 1 plus 2x2 plus is equal to 7, right? x1 times negative 2 plus x2 times 5 is equal to 4. x1 times negative 5 plus x2 times 6 is equal to negative 3. So this is actually just a basic systems equation with two unknowns, three equations with two unknowns. If you can solve it, then you can find the linear combination. Linear combination means adding them to get to a new vector. Likewise, I can say otherwise. I have a system of equation. Oh, this is add. Can I write it as a vector equation? I can write it as a vector equation. I would think of all the x1 column as a column vector. This is a vector, and this is a vector. So I would say x1 and then 1, the coefficient is 1, 3, negative 2, plus x2 times the column vector of 4, 3, 8, kind of like the augmented matrix column, right? Plus x3 being the unknown, 2, 5, negative 4, equal to another vector, 3, 4, negative 4. So we don't need to solve. So it's just a practice of showing you, if you have a system equation, you can think of it as a vector equation. If you have a vector equation, it is actually a systems of equation. The two things are actually the same. And if you can solve one, you can solve the other. So I'm going to do the next example in the next video to actually solve what combination can I do with 3 vector to get to the B vector. and it would be solving a system of the equation.